and welcome to Homework 3.15. Today we looked at also considering percent change and what happens with that, and other ways to write that. In this case, we're talking mostly about increases, particularly with interest. All right, so let's look at in 2011, the population of deer in a forest was 650. In 2012, the population increases by 15%. Write an expression using only multiplication that represents the deer population. So here we are just writing the expression. It is increasing, which means it's going up. So it's going to be 100% of this amount plus that 15%. So we can multiply it by 1.15, which is 115%. You can also think of that as 650 times 1 plus 0.15 because you're multiplying it times 1, which gives you itself, right? That's the original amount, plus that 15% of 650. So this is the best way to write that using only multiplication. In 2013, the population increases again by 15%. Write an expression that represents the deer population in 2013. So we can write this as 650 times 1.15. That's the first year, right, that has passed. And then we're going to multiply it by that amount again, because now the amount that it had gotten to after that first year is going to increase again by 15%. This can also be written as 650 times 1.15 squared, or to the second power, because this right here is multiplied by itself twice. If the deer population continues to increase by 15% each year, write an expression that represents the deer population T years after 2011. So again, our starting amount was 650 times 1.15 to the power of T, and we'll say f of T, so we give this a full function name. Number 2, Maya and Elena are shopping for back-to-school clothes. They found a skirt that originally cost $30 on a 15% off sale rack. Today, the store is offering an additional 15% off. To find the new price of the skirt in dollars, Maya says they need to calculate 30 times 0.85 times 0.85. Elena says they could just multiply 30 times 0.7. How much will the skirt cost using Maya's method? So if we use Maya's method, we'll have 30 times 0.85, so that gives us the remaining costs. And then we're going to multiply it by 0.85 again, because that is going to give us the remaining cost of that amount. So that would be $21.60, we'll round up to 68 cents. If we use Elena's method, we're going to have 30 times 0.7, which will be 21. And it says, explain why the expressions used by Mai and Elena give different prices for the skirt. Which method is correct? So Mai's is taking an additional 15% off the already discounted price, right? So she's taking 15% off and then taking 15% off again. However, Elena is just combining the percents to be 30% off. So 15% plus 15% is 30%. However, it's taking an additional 15% off the discounted price. So my is correct. My is correct. If it said the store is offering a total of 30% off, then Elena's method would work. But this is an additional 15% off. So it takes the discount and then you take another discount off of the existing discount. All right, number 3, one $1,000 loan charges 5% interest at the end of each year, while a second loan charges 8% interest at the end of each year. Complete the table with balances for each loan. Assume that no payments are made and that the interest applies to the loan balance, including any previous interest charges. All right, so we're not adding anything or subtracting anything here in terms of increasing the loan amount. We're mostly focusing on how the amount of interest is going to increase over time, right? So if we have one 1,000 loan with a 5% interest, after 1 year, it would be 1,000 times 1.05. That's how much it's going to be now that we owe. which is going to be 1050. Now, if it's an 8% interest, then we're going to have 1,000 times 1.08, which you may have also reasoned out is $1,080. Okay, now the next year, you're going to take this amount and multiply it again by 1.05, or, right, because that's the factor here, or we can multiply it by 1,000 times 1.05 squared, right? So this is taking that 1050 times 1.05 again, and now our new amount owed is 1102 and 50 cents. Now I can show you that this works out too. If we write it as 1.05 squared, we will also get the same amount. So here for the 8% interest one, again, we're doing this squared, or again, multiplying this times 1.08. Again, you'll get the same thing. So 1,000 times 1.08 squared gives us 1166.4. Or we can take 1080 and then multiply it by the factor, which is 1.08, and you'll get that same amount, right? So really what we're doing is each time we're taking the amount before and multiplying by that percentage increase. In this case, 105%, 108%. Again, that means because we're multiplying it by the same thing every time, that's why we're able to write it with a exponent. So this is 3 years. This is now 1,000 times 1.08 to the power of 3. And then if we were to replace it with any amount of time, let's say we are going to replace that exponent with, oops, this is 8 to the power of t. Any number of years then can be inserted there. Which loan balance grows more quickly? How will this be visible in the graphs of the two loan functions, balances B and C as functions of the number of years? So loan balance C should be growing more quickly, but let's go ahead and just show that in our graph. So 1,000 times 1.05 to the power of x and 1,000 times 1.08 to the power of x. Now remember, in your calculator, or in your work rather, you might see other variables. In your calculator, always use x and y, okay? Because otherwise the graph's going to get real weird on you, all right? I promise. So we're looking at the blue line being 5% interest and the red line being 8% interest. Let's take a look at it and see what we get. So we can't see this here, and that makes sense because our window is too small. We don't need to worry about negative values. We could think about it over the period of 10 years or so. And then same thing for y, we're not worried about negative values, but our max amount that we know is going to be well over 1,000. So let's make that 2,000 just so we can get an upper point of the graph. Now notice here we said which one's going to grow faster. The red line is in fact going and passing the blue line pretty quickly. If we were to zoom in right here, we would see that. And so loan balance C grows more quickly. And we can see it again in the graph. In the graph, the line increases faster, right? It has a greater slope. Use technology to create graphs representing B and C over time. We've done that. The graph should show the starting balance of each loan as well as the amount of the loan after 15 years. Write down the graphing window needed to show these points. Think about the domain and range. So if we're going to the graphing window and it says 15 years, I am going to change my max to 15 here and then press graph again. So this is giving me more time here. And so X needs to be between 0 and 15. Now our y values, notice at the end here, I can no longer see the red and blue graphs, which means my y value is going to have to increase a bit here. So greater than 0, but then let's go ahead and increase this. Actually, let's go to second table, and let's look and see at 15 years, the highest point, right, which will be graph, the red graph here, or loan C, I believe it was, is 3,100. So for our window then, in order for me to see it, I'm going to need you, let's change it to 3,200 and see what we get. So now we can see both graphs at 15 years. All right, so we'll say between 3,200, something greater than at least 3,172, right? It has to be greater than that. Number 4, Lynn opened a savings account that pays 5.25% interest. So this is 5.25% interest. Written as a decimal, that's going to be 0.0525. Okay, somebody asked me the other day, well, when it's like this with this decimal, how do I write that percent as a decimal? You are simply doing the same thing you always would and moving that decimal point over 2 or, right, dividing by 100. All right, and so this is annually deposited is $5,000. Sorry, it's compounded interest annually and deposited $5,000. If she makes no deposits and no withdrawal for 3 years, how much money will be in her account? All right, so in this case, this is a nice kind of interest. This is the kind of interest where you get paid. Either way, the amount is increasing here. So we're going to multiply times 1.0525 because we are multiplying by itself plus that amount of interest on it. And then it is over 3 years, so to the power of 3. So let's go ahead and calculate that here. So 5,000 times 1.0525 to the power of 3 are cubed, and it's going to be $5,829.57. 5.25% interest is actually a decent amount of interest to earn in a bank. So after 3 years, she's going to make $829 off of this account, right? That's a valuable reason to save money in a bank. All right, number 5, a person loans his friend $500. They agree to an annual interest rate of 5%. Wow, his friend is making money off of him. Write an expression for the computing amount owed on the loan in dollars after T years. So F of T equals $500 times, now again, he's going to owe more on this, so it's increasing 1.05% to the power of T. Number 6, select all situations that are accurately described in this expression, 15 times 3 to the 5th. So we want to see which of these work as a scenario for that expression. A population of bacteria begins at 15,000. The population triples each hour. How many bacteria are there after 5 hours? This could be true. That is absolutely true. Starting at 15, if we're saying that it is in thousands, times 3, so it's tripling, and then after 5 hours, that does work. A population begins at 15,000. The population triples each hour. How many thousand bacteria? Oh, okay, so here actually, this one's better, right? Because this doesn't say how many bacteria, it says how many thousand bacteria are there after 5 hours. So we're looking at assuming that this is in 15,000. C says the population of bacteria begins at 15,000 and quintuples. Quintuples would be times 4. Okay, no, we're multiplying by 3. So that doesn't make sense. A bank account balance is $15. The bank account triples each year. What is the bank account amount balance in dollars after 5 years? That would be fine, starting at 15. All right, and then E says a bank account balance is 15,000. It grows 3,000 each year. What is the bank account balance in thousands of dollars after 5 years? So the thousands of dollars of part works, the 5 years part works, even the 15,000 part. But this grows by 3,000 each year. It's not multiplying, right? It means that we're adding 3,000. This would be a linear function. It is not represented by a, excuse me, I just dropped something, by a exponential function. All right, number 7. Here are graphs of two exponential functions, f and g, where f is 100 times 2/3 the power of x, and g is 100 times b to the power of x. What could be the value of b? So notice that b is depreciating a lot faster than f, which means the fraction amount left is going to be less than 2/3. That means then that a is the only possible answer. 3/4 would mean it's retaining more. It's retaining 75%, so that would be above the line. 1 would mean that is just staying the same. And then 3/2 is 1.5, right? So that would mean that the function is increasing, which it is not. It is depreciating. Number 8, the real estate tax in 2018 in a small rural county increased by 1/4%. In 2017, a family paid $1,200. Which expression represents the real estate tax in dollars that the family will pay in 2018? All right, so the family paid this tax amount, right? That's the real estate tax that they're paying, and it's increasing by 1/4%. So, right, that's 1/4% would be 0.25%. 0.25% in decimal form is moving this decimal over two place values. So we're talking about this amount in a decimal form. Okay, so A would be multiplying by 1/4 of that amount, but it's not saying it's increasing by 1/4, it's increasing by 1/4%. So that is not accurate. B is, again, if we were multiplying by 25%, we're not talking about 25%, we're talking about 1/4%, which is even smaller. So we're looking at D, right? Because here is where we would add that 1 here, 1.0025, and in this case, we're increasing by that. It's a very, very small percent. 1/4% is 0.25%. Tiny, tiny amount. All right, our last one is a review. Two inequalities are graphed on the same coordinate plane. Select all the points that are solutions to the system of inequalities rather. So remember, the solutions are only in this shaded area that is double shaded. Shaded by this one and shaded by this one. And it does not include the dotted line points. It does include the solid line points. All right, so 4 comma -6 would be here exactly on this point right here. Now it is on a solid line for that one line, but it's on a dotted line for the other one. So this would not be a solution that works for both inequalities. 4 comma 6. So 4 comma 6 is up there. That does not work for both of them. -4, -6, also going to be down over here. Down over here rather, doesn't work for both of them. -4 comma 6. So -4 up here, that makes no sense. It's not in either of the shaded areas. 6 comma -8. Okay, so now we're talking. 6 comma -8 is right there in the thick of it. That one is going to work. 7 comma -9, also right here in the middle there, going to work. -8 comma 6, already just looking at that, I can tell that's up here. That does not work. All right, that is your homework help for today. I am going to go back up to the classwork really quick, but if you want to stop here, you can. Your code word for today will be paper towel, since your parents so generously donated some paper towel to our classroom. So in this part of comparing average rate of change, remember that is slope. And remember that slope is the distance of your y values over your x values if you were to draw a triangle, right? This is a little bit of a review because I've noticed we're still, some of us, not quite sure about slope. But we're calculating the difference over time when we're talking about average rate of change in terms of our exponential functions. And so I've written for each of these here, kind of started that for you. It's over 2 years. If it's the start of the loan and the end of the second year, that's over 2 years, right? So dividing by 2. And then we're looking at the starting amount in these loans, if we go back in this problem, was $1,000, right? So we're subtracting 1,000 because that's the original amount. And then we need to see what we would be at after 2 years. So after 2 years, if it's a 12% loan and we're starting at 1,000 times 1.12 squared, right? Because this is after 2 years. So the amount we would have then that we would owe is 1254.4. So 1254.4 minus 1,000 and then divided by those 2 years. So that's 127.2. That means on average, we are going to be owing $127.20 per year. All right, and so then here now we're looking at if we were talking about the second loan is 24%. So 1,000 times 1.24 to the power of 2 gives us 1537.6 minus 1,000 divided by 2 gives us 268.8. All right, so again, that's the increasing amount that we're owing every time. Now in this last one, our last scenario, loan C is 30.6. That's a lot. Okay, so 1,000 times, if you get a loan and you owe 30% interest, that's a lot of interest, y'all. Okay, so that's a bad loan. All right, but squared 1705, 1705.64 we'll say. So minus 1,000 divided by 2 gives us 352.81. So loan C, you can see that over time, over those 2 years, you're going to owe a lot more, right, than loan A. So for this second part, it says the end of the 10th year and the end of the 12th year. So here we're looking again divided by 2 because we're talking about the difference of 2 years. Okay, and the time is our input, so that's going to go into our denominator. But then we're thinking about the 10th year and the end of the 12th year. So if the first equation was, I believe, let's go back so I can make sure, is 12%. We're looking at $1,000 times 1.12 to the power of 12, right? Minus, because that's after 12 years, we want to do minus over 10 years, 1,000 times 1.12 to the power of 10 years. Well, let's see what we get here. So here we get 790, and then we're going to divide by 2. And so here we'll owe $395.06 per year from year 10 to year 12. All right, now if we're looking at the second loan, which was 24%, a much greater percent, we're going to do the same thing. So 1,000 times 1.24 to the power of 12 minus 1,000 times 1.24, same interest percent, but this time to the power of 10. So that's how much we would owe in year 10. So now we're looking at 4,620 and 36 cents divided by 2, those 2 years, 2310. That's a lot, right? That's a lot of money that you're going to be owing over those 2 years when you're in year 10 and 12. So this is showing you that exponentially that amount is increasing so much faster than A. And then in scenario C, I believe it was 30 some percent, right? Yes, 30.6. Whew. 1.306 to the power of 12. Use our over button minus 1,000 times 1.306 to the power of 10. This is going to be a much larger amount. Yep, divided by 2 gives us 5090. Oh, I'm sorry. Hold on. I put that in the wrong place. I went ahead and did too much there. All right, so this is what $10,186.21 approximately. Over 2 years is going to be an average of $5,093.10 per year between years 10 and 12. All right, it says, how do the average rates of change for the 3 loans compare in each of the 2-year intervals? So the average rate of change is much greater as the percent of interest increases. Interest increases, right? So the more interest we owe, then the greater those leaps are between years as that function increases. As we get to years 10 and 12, the amount of interest that we're going to then owe is going to be so much more because we're paying interest on those previous year's amounts. All right, that is all. If you need any assistance, please feel free to reach out. Happy homeworking and see you tomorrow.